I want to begin with a thought experiment that I have been returning to for 30 years, and that I have never found a completely satisfying way to escape. Imagine that you are reading a book, not this conversation, an actual physical book printed on paper, bound between covers. You are somewhere in the middle, perhaps a third of the way through, and you are deeply absorbed in the story. The characters feel real. The world the author has constructed has texture and history and weight. And then someone tells you something you did not know. They tell you that they have already read the entire thing, that the final page has already been written, that the last sentence is already there, fixed and permanent, existing in the physical object you are holding, in the pages you have not yet reached. Does that knowledge make the chapter you are in less real? Does the vividness of the characters diminish? Does your absorption in the story become somehow illegitimate because the ending already exists? Most people, when they think carefully about this, say no. The existence of the ending does not retroactively negate the reality of the middle. The story is a complete thing. It exists as a whole. Your experience of reading it is a temporal journey through a complete structure that already exists in its entirety. The last page does not make the page you are on less present, less immediate, less real. I want to apply this thought experiment to the universe, not as a metaphor, as a precise physical claim. The universe has an ending, not a speculative ending, not one that might or might not occur depending on conditions we have not determined. A determined, physically derivable, mathematically precise ending that follows from the laws of physics and the initial conditions of the cosmos with the same certainty as any prediction science has ever made. The universe will end in a state that physicists call the heat death. And the heat death in the space-time block that special relativity and general relativity together describe already exists. It is at a specific temporal location in the four-dimensional structure of space-time. It is the last page of the book. It is already there in the part of the structure you have not yet reached. You are in the middle of the book right now, in the chapter where stars still shine and complexity still exists and minds can still form and ask questions. You are living in the echo of the extraordinarily ordered beginning, the echo that began with the Big Bang and that will eventually, inevitably, fade into the silence of maximum entropy. The echo is real. It is vivid. It is where everything interesting has happened and is happening. And the fact that it will eventually fall silent, that the last page already exists in the block, does not make this page less real while you are reading it. That is the central claim of this conversation. And I want to take you through it with the full precision and the full depth it deserves, because most discussions of the fate of the universe stop too early. They describe the ending and leave you with a vague sense of cosmic melancholy. What I want to do is go further. I want to show you not just what the ending looks like, but why it was always going to happen, why the beginning required it, what the physics of the ending tells us about the nature of the universe we are in right now, and what it means, in a precise physical and philosophical sense, to live inside a story that has already been completely written. Let me start with the ending itself, because I think you need to understand what it looks like in full detail before you can appreciate what I want to say about it. The second law of thermodynamics is one of the most fundamental principles in all of physics. It says that in any isolated system, the total entropy, the measure of disorder, never decreases over time. Entropy can stay the same. It can increase, it cannot decrease. This is not a strict law in the way that conservation of energy is strict. It is a statistical statement about the overwhelmingly probable behavior of systems with very large numbers of degrees of freedom. But when the number of degrees of freedom is as large as it is in macroscopic systems, let alone in the universe as a whole, overwhelmingly probable, is so close to certain that the distinction barely matters. What is entropy really? I want to spend time on this because the concept is central to everything else I am going to say, and the usual explanations are either too vague or too technical. Entropy is a measure of the number of microscopic ways a macroscopic state can be realized. Consider a glass of water. The macroscopic state is described by familiar quantities: temperature, pressure, volume. The fact that it is liquid water. The microscopic state is the exact position and velocity of every molecule in the glass. There are an astronomically large number of microscopic states that all correspond to the same macroscopic state. The entropy of the macroscopic state is proportional to the logarithm of the number of microscopic states that correspond to it. A highly ordered macroscopic state, a crystal, a living organism, a galaxy with its structured spiral arms, corresponds to a relatively small number of microscopic configurations. The constraints imposed by the ordered structure reduce the number of ways the system can be arranged microscopically. A disordered macroscopic state, a gas dispersed uniformly through a volume, a pile of ashes, a lukewarm mixture, corresponds to an enormously larger number of microscopic configurations. The reason entropy tends to increase is purely statistical. At any given moment, a system is overwhelmingly likely to transition into a state with higher entropy simply because there are so many more such states available. The increase of entropy is not driven by any force or any law. In the fundamental sense, it is driven by counting. High entropy states are so vastly more numerous than low entropy states that random evolution almost always moves toward them. Now apply this to the universe as a whole. The universe has a vast number of possible states it could occupy. The total number of accessible states is so large that even writing it as a power of 10 would require more digits than there are atoms in the observable universe. And the vast majority of those states are high entropy states, featureless, disordered, structureless, undifferentiated distributions of matter and energy at uniform temperature. The universe we observe is not in one of those high entropy states. It is in a state of remarkable order. There are galaxies with structure and angular momentum and complex internal dynamics. There are stars, burning hot, concentrated spheres of plasma separated by vast, cold voids. There are planets with solid crusts and liquid oceans and gaseous atmospheres. There is life, extraordinarily low entropy configurations of matter that maintain their order by consuming energy and exporting entropy to their environments. There is consciousness, the most elaborately organized process we know of, maintaining patterns of neural activity against the constant pressure of thermodynamic dissipation. All of this order, all of this structure, all of this complexity exists because the universe began in a state of extraordinarily low entropy. This is the central fact about the beginning of the universe from the thermodynamic perspective, and it is, I think, the most important fact about the universe that most people do not know. The Big Bang was not just the beginning of time and space. It was the beginning of a thermodynamic gradient, an extraordinarily large gap between the entropy of the current state and the maximum possible entropy, a gap that has been driving every physical, chemical, and biological process in the universe for the past 13.8 billion years. Roger Penrose has calculated the probability of the initial state of the Big Bang occurring by chance, given any reasonable prior probability distribution, over possible states of the universe. His answer is approximately 1 in 10 to the power of 10 to the power of 123. I want you to try to feel the magnitude of that number, even though I know it is impossible to truly feel it. The number of atoms in the observable universe is approximately 10 to the 80. 10 to the 80 is a large number. But 10 to the 10 to the 123 is so incomprehensibly larger than 10 to the 80 that no analogy can bridge the gap The Big Bang's initial conditions were not just unlikely, they were by any ordinary measure of probability impossible, and yet they happened. This extraordinary improbability of the beginning is sometimes cited as evidence for a creator or a designed universe. I am not going to make that argument. It is not a scientific argument. But I am going to take the improbability seriously as a physical fact because it tells us something important about the relationship between the beginning and the ending of the universe. The beginning was extraordinarily ordered. The ending will be maximally disordered. The entire history of the universe, from the first instant to the last, is the story of the entropy gradient created by that extraordinarily improbable beginning being exhausted slowly over timescales that make human history look like an eye blink. Every star, every planet, every organism, every thought, every moment of beauty or understanding is a local feature of that gradient. A temporary eddy of low entropy in the inexorable flow from the improbable ordered beginning to the certain disordered end. You are one of those eddies. The specific configuration of matter and energy that constitutes your body, your brain, your mind, is a low entropy structure maintained against the gradient. You are not fighting the gradient. You are part of it. You are the gradient doing something with itself in a particular region of space and time. And the ending, the heat death, is the state in which that thermodynamic activity, that local entropy maintenance, is no longer possible anywhere in the universe. The gradient has been exhausted. Now let me take you through the timeline of how that happens, because the specific stages and the specific numbers are important. They are the most extraordinary sequence of timescales in the history of science, and I want you to feel their scale. We are currently in what cosmologists call the Stelliferous Era, the age of stars. The observable universe contains approximately 2 trillion galaxies, each containing hundreds of billions of stars. The Sun is roughly halfway through its 10 billion year main sequence lifetime. The most massive stars burn out in millions of years. The least massive, the red dwarfs, will continue burning for trillions of years. The Stelliferous Era will last approximately 100 trillion years, or 10 to the 14th years. The current age of the universe, 13.8 billion years, is about 10 to the 10th. We are roughly 1/10,000th of the way through the Stelliferous Era. In the remaining duration, more stars will be born and die than have existed in all of cosmic history to date. But the stellar activity is already declining. The peak of star formation in the observable universe occurred about 11 billion years ago, roughly 2 billion years after the Big Bang. Since then, the rate has been falling. As the gas that fuels new star formation is gradually consumed or heated beyond the threshold for gravitational collapse, we are on the declining slope. The universe is already past its most productive era in terms of stellar birth. I want to pause here because I think this deserves emphasis. We tend to think of the current universe as a busy, active, star-forming cosmos in its prime. But by the standards of its own history, the universe is already aging. The era of peak stellar activity is 11 billion years in our past. The universe in which we live is not the young, maximally productive universe of the early Stelliferous Era. It is a middle-aged universe past its peak, producing fewer new stars each year than it did in its youth, with galaxies whose gas supplies are gradually depleting. This is not cause for despair. A middle-aged universe still contains an enormous number of stars. The observable universe right now has more stars than there are grains of sand on all the beaches of the Earth, roughly 10 to the 24. The decline is slow. The Sun has 5 billion years of main sequence life remaining. The red dwarf stars that will be the last to burn have trillions of years ahead of them. The decline from the peak to the end of the Stelliferous Era is so slow that it is invisible on any human timescale, but it is happening. And knowing that it is happening changes the context of the current moment. We are not at the beginning of the story of stars and complexity. We are somewhere in the middle of the decline from the peak. The universe has been building complexity for 13.8 billion years and will continue for trillions more, but the rate of building has been slowing for the past 11 billion years. We are living in the long, slow, gradual dimming of a universe that burned brightest billions of years before we arrived. There is something poignant about this that I want to acknowledge. The most active, the most productive, the most star-rich epoch of the universe is already in the past. The galaxies we observe today are quieter than the galaxies of 3 billion years ago, which were quieter than the galaxies of 8 billion years ago. The quasars, those extraordinarily energetic objects, powered by rapidly accreting supermassive black holes that dominated the early universe, are mostly quiet now. The intense star formation that built the bulk of the stellar mass in the universe occurred long before the solar system existed. We live in the afterglow of the universe's most energetic epoch, watching the embers of a fire that burned brightest when the cosmos was young. And yet this afterglow is the context in which life emerged. The very fact that the universe is in this quieter, later epoch is part of what makes it hospitable to life as we know it. The extreme violence of the early universe, with its intense radiation and rapid stellar evolution and frequent supernovae, may have been inimical to the long-term stability that complex chemistry and biology require. We are here because the universe has quieted enough for stable planetary systems to exist for billions of years. The decline is also a settling, and the settling made us possible. Eventually, the gas runs out. The existing stars burn out one by one. The last stars in the universe will be red dwarfs, small and cool, burning hydrogen so slowly that they will shine for 10 trillion years before exhausting their fuel. They will not explode. They will simply cool slowly into dark, dense remnants. The Stelliferous Era will end in darkness, not a dramatic darkness. A gradual, star-by-star darkening that takes trillions of years and that no observer will experience as a single event. After the last star goes out, the universe enters the Degenerate Era, the era of stellar remnants, white dwarfs, the dense crystallized cores of stars like our Sun that ended their lives without exploding. Neutron stars, incredibly dense objects, where more than a solar mass is compressed into a sphere 20 kilometers across. And black holes, the remnants of the most massive stars, objects so dense that nothing, not even light, can escape their gravity. These remnants cool on timescales that challenge any human concept of duration. A white dwarf composed of carbon and oxygen takes approximately 10 to the 37th years to cool to near absolute zero. The current age of the universe is 10 to the 10th. The ratio between those two numbers, 10 to the 37th divided by 10 to the 10th, is 10 to the 27th. The cooling time of a single white dwarf, measured in units of the current age of the universe, is itself a number larger than the number of atoms in the Earth. But the Degenerate Era is not the final era. Something else will end it before the white dwarfs finish cooling. That process is proton decay. Proton decay is predicted by virtually every grand unified theory of particle physics, the theoretical frameworks that attempt to unify the strong nuclear force with the electroweak force into a single description. These theories predict that the proton, which we ordinarily treat as stable, actually has a finite lifetime and will eventually decay into lighter particles. We have not yet directly observed proton decay. The current experimental lower bound on the proton lifetime is approximately 10 to the 34th years. The predicted lifetime in most grand unified theories is somewhere between 10 to the 34 and 10 to the 40 years. On those timescales, every proton in the universe will eventually decay. The solid material of white dwarfs and neutron stars, The carbon and oxygen and iron that makes up the bulk of the degenerate era's matter will gradually disintegrate. White dwarfs will evaporate, not through cooling, but through the radioactive decay of their constituent particles. The degenerate era ends when the last ordinary matter has dissolved into its elementary components. After proton decay has consumed all ordinary matter, only black holes remain. They do not decay through proton decay. They are not made of ordinary matter. They are made of space-time curvature, and they evaporate through a completely different mechanism, Hawking radiation. In 1974, Stephen Hawking showed that quantum effects near the event horizon of a black hole cause it to emit a slow, cold stream of radiation, losing mass gradually until it evaporates completely. The evaporation time of a black hole scales as the cube of its mass. A black hole with the mass of the Sun takes approximately 10 to the 67 years to evaporate. The supermassive black holes at the centers of galaxies with masses of billions of solar masses take approximately 10 to the 99 years. 10 to the 99. If you wrote this number out in full, it would have 100 digits. The number of atoms in the observable universe has 80 digits. The evaporation time of a supermassive black hole is a number with more digits than there are atoms in the observable universe. I want to pause here and ask you to do something. I want you to try to feel the ratio between 10 to the 99 and 10 to the 10, the ratio between the evaporation time of a supermassive black hole and the current age of the universe. The ratio is 10 to the 89. The number of atoms in the observable universe is 10 to the 80. So the evaporation time of a supermassive black hole, measured in units of the current age of the universe, is roughly 10 times the number of atoms in the observable universe. There's no analogy adequate to this. The human mind did not evolve to hold numbers of this magnitude, but the numbers are real. The physics is real, and the timeline is not a speculation. It follows from equations that we have tested to extraordinary precision in every regime we can access. I want to say something about what the black hole era actually looks like, because I think most people, when they hear that black holes will eventually evaporate, imagine a dramatic event, a final flash, a last burst of energy marking the end of the universe's most enduring structures. The reality is more subtle and more strange. The Hawking radiation from black holes at the scales relevant to the black hole era is extraordinarily faint. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. A black hole with the mass of 1 billion suns radiates at a temperature of approximately 10 to the minus 17 Kelvin. That is a 10 with 17 zeros after the decimal point. Far, far colder than the cosmic microwave background today, and incomprehensibly colder than anything we associate with heat in everyday experience. This radiation is so faint that it cannot be measured by any instrument we could ever build, and it will not be measurable by any instrument in the black hole era either, because even the quantum noise of the late universe will overwhelm it. The evaporation of a black hole in the black hole era is not a bang. It is the slowest possible whisper, a barely perceptible diminution of mass over timescales that swallow every human concept of duration. And at the very end, in the last moments of evaporation, when the black hole has lost most of its mass and its Hawking temperature has risen above the temperature of the surrounding environment for the first time, the evaporation accelerates. The final moments of a black hole's existence are more energetic than the billions of years that preceded them. A brief, modest burst of energy, and then nothing. The black hole is gone. A small contribution of photons and particles to the ever more diffuse cosmic gas. And the universe continues, dimmer by one small, very cold source of radiation. This is not a single event. It happens once for every black hole that formed over the universe's entire history, each evaporation separated from the others by intervals of time that dwarf the interval between now and the formation of the first black holes. The black hole era is not a single story. It is a vast collection of independent endings, each one isolated from the others by distances and timescales that make any concept of communication or observation between them meaningless. The universe in the black hole era is not a place. It is barely even a setting. It is a sparse, cold, slow dispersal of matter and radiation in an expanding space, punctuated at incomprehensibly rare intervals by the final evaporation of a black hole that has been cooling and shrinking for longer than the universe has currently existed. And after the last black hole evaporates, after its final quantum of Hawking radiation disperses into the expanding, cooling universe, the universe enters its final state, a thin, cold, expanding gas of photons, electrons, positrons, and neutrinos. The temperature is a fraction of a degree above absolute zero, approaching but never reaching the true zero that quantum mechanics forbids. The density is so low that the average distance between particles is measured in light years. Nothing is happening. No gradients, no structures, no processes, no information being processed, no entropy left to increase. This is maximum entropy. This is the heat death. This is the last page. From that state, there is no spontaneous return to complexity. The second law ensures it. The high entropy final state is, for all practical purposes, the permanent state of the universe for the rest of time. But I said for all practical purposes, and I want to take that qualifier seriously, because there is a theorem in mathematics that complicates the picture in a way that I find genuinely important. In 1890, the French mathematician Henri Poincaré proved that any bounded mechanical system with reversible equations of motion will, given enough time, return arbitrarily close to its initial state. The Poincaré recurrence theorem says that the universe, if it is finite and if its quantum mechanical evolution is unitary, will eventually fluctuate back to a low entropy state comparable to the Big Bang. Not once, infinitely many times, each recurrence separated from the previous by an interval of time that makes 10 to the 99 look like an instant. The Poincaré recurrence time for the observable universe is approximately 10 to the power of 123 years. This number is so large that it cannot be related to any physical quantity in any meaningful way. But it is a finite number, and that matters philosophically, even if it matters nothing practically. The Poincaré recurrence theorem has a disturbing implication that has occupied physicists since it was first noticed by Boltzmann himself. If the universe persists in or near thermal equilibrium for long enough, random fluctuations will occasionally produce local low entropy structures. Most fluctuations are tiny. But given enough time, fluctuations of any size occur, including fluctuations large enough to produce a functioning human brain, complete with false memories of a complex universe, arising spontaneously from thermal noise. These hypothetical, spontaneously generated brains are called Boltzmann brains, and they present a serious philosophical problem. In a universe that exists near thermal equilibrium for an extremely long time, the number of Boltzmann brains generated by thermal fluctuations vastly exceeds the number of ordinary brains that evolve through normal biological processes. If we are to consider ourselves typical observers, we should expect to be Boltzmann brains, because they will exist in vastly larger numbers than ordinary brains over the long history of the universe. But if we are Boltzmann brains, all our memories are false. The universe we seem to be living in is an illusion. We have been spontaneously generated, fully formed with false memories, and we will dissolve back into thermal noise in an instant. This conclusion is absurd. And the fact that statistical mechanics and the long future of the universe together imply it as a sign that something in the reasoning is wrong. The problem is taken seriously enough that it is used as a constraint on cosmological models. A model that predicts the production of vastly more Boltzmann brains than ordinary brains is considered pathological, because it would mean that the vast majority of observers in the universe are Boltzmann brains with false memories, making scientific knowledge systematically unreliable. The most natural resolution is to restrict the relevant population of observers to the Stelliferous Era, the era when ordinary star-supported life is possible, rather than treating the entire infinite future as equally relevant. If we count only observers who exist during the Stelliferous Era, the Boltzmann brain problem dissolves. But let me stay with the Boltzmann brain problem a little longer, because I think it is pointing at something important about the nature of knowledge and reliability that goes beyond its specific application to cosmology. The reason the Boltzmann brain problem is considered a problem, rather than just an interesting mathematical curiosity, is that it threatens to undermine the reliability of scientific knowledge. If we could be Boltzmann brains with false memories of a complex universe, then the entire enterprise of science, which depends on the assumption that our memories of past observations are reliable, would be called into question. We would have no way of distinguishing genuine scientific knowledge from the false memories of a spontaneously generated brain. The problem is self-undermining. We cannot use scientific reasoning to determine whether we are Boltzmann brains, because if we are, our scientific reasoning itself is unreliable. The way physicists actually deal with this problem is not by proving we are not Boltzmann brains. We cannot prove that. It is by treating the Boltzmann brain concern as a constraint on cosmological models. We require that any proposed model of the universe not place us in a situation where we are more likely to be Boltzmann brains than ordinary observers. This is a methodological choice, a decision about what kinds of physical theories we are willing to consider, motivated by the self-undermining nature of the Boltzmann brain conclusion. It is, at bottom, a way of saying we are going to assume that our memories and observations are reliable, and we are going to reject cosmological models that imply they are not. This methodological choice has real consequences for cosmology. It rules out some models of eternal inflation in which the vast majority of observers are Boltzmann brains. It motivates the search for a cosmological model in which ordinary observers like us are statistically typical, not exceptional. And it connects to the deeper question of what determines the boundaries of the relevant population of observers, the reference class problem, which is one of the most difficult and most consequential problems in the foundations of cosmological reasoning. I raise all of this not to solve the problem, but to illustrate the kind of philosophical depth that the question of the universe's ending opens up. When you ask seriously about the heat death, about the long future of the universe, about what it means to live in the middle of a complete story, you are not just asking about astronomy. You are asking about the reliability of knowledge, the nature of consciousness, the definition of a typical observer, and the self-referential relationship between the reasoning mind and the universe it is trying to understand. But the Boltzmann brain problem points at something important beyond its specific technical content. It tells us that the long future of the universe is qualitatively different from the present era in ways that challenge our intuitions about physics and existence. In the Stelliferous Era, the universe is full of structured, complex, far from equilibrium systems, stars, planets, organisms, minds. These systems are sustained by the entropy gradient between the hot interiors of stars and the cold surrounding space. In the eras that follow, after the gradient is exhausted, these things cease to exist. The concept of a stable physical system with a consistent history no longer applies. The long future of the universe is not more of the present, extended in time. It is qualitatively different. And the Stelliferous Era, the era of complexity and life, is a specific phase with specific beginning and specific end. Now I want to bring in the space-time block, because I think it changes the significance of everything I have described in a way that is philosophically important and physically precise. In special relativity, as I discussed in the earlier video about the moment of your birth, the universe is described as a four-dimensional space-time structure, a block in which every event at every time exists with the same ontological status. The past, the present, and the future are all equally real features of the four-dimensional block. The heat death exists in the block at its specific temporal location. The Big Bang exists in the block at its specific temporal location. And your life, the specific world line that traces your existence from birth to death, exists in the block between them. This means something precise. The heat death does not erase the Stelliferous Era. It comes after it in the temporal direction, but it does not reach back and undo it. The moments of complexity and awareness and understanding that occurred in the Stelliferous Era are permanent features of the block. They are as real as the heat death. They are as permanent as the heat death. No subsequent event in the universe can remove them from the block. The second law of thermodynamics moves forward in time but does not edit the past. The past is the most permanent thing in the universe. This is what I mean when I say that the echo is real. The echo, the Stelliferous Era, the age of stars and life and minds, is in the block permanently. The silence of the heat death is also in the block at its temporal location, but the echo is there too, at its temporal location, and neither can undo the other. The book is complete. Both the interesting middle and the silent ending are features of the complete structure, and the complete structure is what it is. I want to dwell on the extraordinary improbability of the middle because I think it is one of the most underappreciated facts about the universe. The Stelliferous Era is not a generic feature of any universe with a low entropy beginning. It is a feature of a universe with a very specific set of fundamental constants. Consider just a few examples. The triple alpha process, the nuclear reaction by which 3 helium nuclei combine to form carbon in stellar interiors, depends on a specific energy level of carbon 1-2. If that energy level were a few % different in either direction, carbon would not be produced in significant quantities in stellar interiors. Without carbon, there is no organic chemistry. Without organic chemistry, there is no life as we know it. The specific energy level of carbon, 1-2, is either an extraordinary coincidence or a reflection of something about the structure of physical reality that we do not yet understand. The cosmological constant, the energy density of the vacuum that drives the accelerating expansion of the universe, is another example. The theoretical prediction for the cosmological constant from quantum field theory is approximately 10 to the 120 orders of magnitude larger than the observed value. Something is canceling the vacuum energy almost perfectly, leaving only a tiny residual. If the cosmological constant were not as small as it is, the universe would have expanded too rapidly for galaxies to form, or collapsed back on itself before complex structures could develop. The specific value we observe is precisely in the range that allows the formation of the structures that make the middle of the story possible. This accumulation of specific, precise, necessary conditions for the existence of the Stelliferous Era is sometimes described as fine-tuning. I am cautious about that language because it suggests intentionality. But the physical fact it points at is real. The middle of the story is not just improbable because of the low entropy beginning. It is improbable because the laws of physics, the specific values of the fundamental constants, happen to be precisely in the range required to convert that low entropy beginning into the complex, structured, life-supporting era we inhabit. Slightly different constants, and the gradient between beginning and ending would exist, but would produce nothing interesting as it was exhausted. Stars would not form, or would burn out immediately, or would not produce the heavy elements that make chemistry possible. The Stelliferous Era requires the beginning to be extraordinarily ordered and the constants to be precisely tuned. Both conditions are met. Both are, in any naive, probabilistic sense, extraordinarily unlikely. Whether this reflects anthropic selection in a multiverse, deeper physics we have not yet discovered, or simply an extraordinary coincidence, I do not know. Nobody knows. But I want to stay with the physical fact a moment longer, because I think it deserves acknowledgement in its own right before we move to the philosophical implications. The ratio of the electromagnetic force to gravity determines the size of stars. If gravity were significantly stronger relative to electromagnetism, stars would be smaller and burn much faster, leaving little time for planetary systems to form and for life to develop. If gravity were significantly weaker, gas clouds would not collapse into stars at all. The specific ratio we observe produces stars that burn steadily for billions of years, long enough for the chemical and biological evolution that produced us. This ratio is not predicted by any current theory. It is an input, a fact about our universe that we have measured but not explained. The ratio of matter to antimatter in the early universe is another example. The Big Bang should have produced equal amounts of matter and antimatter. If it had, every matter particle would have found an antimatter partner and annihilated, leaving a universe of pure radiation with no matter to form stars or planets or chemistry. Instead, for reasons that particle physics cannot yet fully explain, there was a slight excess of matter over antimatter in the early universe. Approximately 1 extra matter particle for every billion matter-antimatter pairs. That tiny asymmetry is what we are made of. All the matter in the observable universe is the 1 in a billion survivor of the initial annihilation. The specific size of that asymmetry is not predicted by any theory we have. It is a fact about our universe that the middle requires and that we do not understand. The list continues. The mass of the Higgs boson, which determines the masses of all fundamental particles. The strength of the strong nuclear force, which determines whether nuclear fusion in stars produces the heavy elements necessary for chemistry. The specific ratio of dark matter to ordinary matter, which determines the rate of structure formation and the size of the galaxies that formed. In each case, the value we observe is in the range required for a universe with a long, complex, structured Stelliferous era. And in each case, the value is not predicted by any deeper theory. It is an input. I am not going to resolve the question of whether this is fine-tuning in the sense of intentional design, anthropic selection, or a yet-to-be-discovered deeper explanation. That question sits at the boundary of physics and philosophy, and I do not think it is currently answerable by the tools of either. What I am going to say is that the physical fact is real. The middle is improbable not just because of the low entropy beginning, but because of the specific values of the constants that determine how that beginning evolves. And the fact that you are in the middle, that the echo is ringing, that the complexity exists, is a consequence of all of those conditions being simultaneously met. The fact that the conditions are met, that the middle exists, that you are in it, is the most remarkable feature of the complete story. More remarkable than the beginning, more remarkable than the ending. The beginning is just an extraordinarily improbable state. The ending is just a maximally probable state. The middle is the specific, elaborate, complex, self-aware consequence of the improbable beginning, made possible by the precise values of the constants unfolding over billions of years in a gradient that has produced everything. Now I want to address the relationship between the ending and the question of meaning, because I think the physics has something important and specific to say that usually gets left to philosophy. There is a response to the knowledge of the heat death that I call cosmic despair. If the universe will end in maximum entropy, if all structure will dissolve, if every achievement and every work of art and every moment of understanding will eventually be dispersed into the thermal noise of the final state, then nothing matters. Everything is temporary. Everything is doomed. The significance of any action or any experience depends on its persistence, and nothing ultimately persists. This response has emotional logic. We often implicitly justify the significance of our actions by their consequences, by what they leave behind. We write books because they will outlast us. We plant trees because future generations will benefit. We build institutions because they will persist. If nothing ultimately persists, the implicit justification seems to evaporate. But I think this reasoning contains a flaw that the space-time block picture helps identify precisely. The flaw is the assumption that the significance of an experience or an achievement is determined by its duration, by how long it persists in the forward time direction. That assumption feels intuitive, but it is not self-evident. And the space-time block picture gives us a way to challenge it with physical precision. In the space-time block, every moment exists permanently, not in the sense of lasting forever forward in time from its location, in the sense of being an indestructible feature of the four-dimensional structure. The moment of your understanding of something beautiful is in the block. The moment of genuine connection with another person is in the block. The moment of creativity, of making something that did not exist before, is in the block. These moments do not cease to exist when they are over. They are over in the temporal sense, meaning your world line moves away from them along the time dimension. But they remain in the block. They are as permanent as any feature of physical reality, as permanent as the heat death itself. The heat death does not erase those moments. It cannot erase them any more than the present can erase the past. The past is in the block. It is there, immovable, indestructible. No subsequent event, not even the maximum entropy final state of the universe, can reach back into the block and remove events that have already occurred. The second law increases entropy going forward. It does not undo the past going backward. The past is the most permanent region of the space-time block because nothing can change it. This means that the significance of an experience cannot coherently be measured by whether it will ultimately persist in the forward time direction. There are two kinds of permanence: lasting forever forward in time, which nothing ultimately achieves, and being an indestructible feature of the space-time block, which every event automatically is. We tend to seek the first kind and assume that without it, existence is transient and therefore less real. But the physics says the second kind is available to everything that happens, automatically, without effort, without exception. Every moment of your life is permanently in the block. The heat death cannot reach it. The second law cannot undo it. The silence that comes after the echo does not erase the echo. The echo has echoed, and in echoing has left its mark on the permanent four-dimensional structure of everything. I want to make this as concrete as I can because I think the abstraction of the space-time block can feel remote from the specificity of lived experience. Think of a specific moment in your life, a moment of genuine joy or of deep understanding or of real connection with another person. That moment occurred. It is in the past. From your current position in the space-time block, moving forward along your world line, that moment is behind you. It is inaccessible. You cannot return to it. The causal structure of space-time, the light cones that determine what can influence what, prevents it. In that sense, the moment is gone, but it is not gone from the block. The block does not have a moving present that consumes the past. The block is static. The four-dimensional structure simply is. Every event in it simply is at its location in the four-dimensional coordinates. The moment you are thinking of is at a specific location in the block. That location is as real as any other location. The heat death at its temporal location is real. Your specific moment at its temporal location is equally real. Neither is more real than the other. Neither can erase the other. The second law of thermodynamics increases entropy moving forward in time. It does not decrease the reality of events in the past. It does not reach into the past region of the block and scramble the events there. The past is untouched by the second law, because the second law is a statement about the direction of change, not about the existence of what has already occurred. Change moves toward higher entropy, but what has already occurred at past temporal locations in the block does not change. It is fixed, permanent, beyond the reach of thermodynamics. This is, I think, one of the most important implications of the space-time block picture for the question of meaning. The significance of a moment cannot be erased by what comes after it. The second law will increase the entropy of the universe going forward, eventually exhausting the gradient and producing the heat death. But it cannot reduce the reality of the moments in the past region of the block where the echo was ringing. Those moments are there permanently. And the meaning of those moments, whatever it is not diminished by their temporal distance from the present or by the eventual approach of the heat death at the other end of the timeline. Every moment of your life is permanently in the block. The heat death cannot reach it. The second law cannot undo it. The silence that comes after the echo does not erase the echo. The echo has echoed, and in echoing has left its mark on the permanent four-dimensional structure of everything. I want to follow one more thread before we approach the end of this conversation. The question of what happened before the Big Bang. I have been describing the story as if it has a clear beginning, a first page before which there is nothing. But honesty requires complicating that picture, because the complication opens one of the most extraordinary vistas in theoretical physics. When we say the universe began with the Big Bang, we mean something specific. We mean that the space-time geometry that describes our observable universe becomes singular approximately 13.8 billion years ago in the past direction of our timeline. The singularity, the point of infinite density and temperature that classical general relativity predicts at the beginning, marks the edge of the description. Beyond it, the classical equations break down. General relativity, as a mathematical framework, cannot be trusted in the regime of the singularity. But the singularity is not the beginning of everything. It is the edge of the description. It is the point at which our current theoretical tools become inadequate. The Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the 1980s, proposes that the geometry of space-time closes smoothly at the beginning, the way the surface of the Earth closes smoothly at the South Pole. In this picture, there is no singularity in the technical sense. The geometry becomes compact and smooth. Time itself emerged along with the geometry from this no-boundary quantum state. There was no time before the beginning because time is part of what began. The question of what came before the Big Bang is not answered by this proposal, but dissolved. There was no before, because before requires time, and time began with the universe. Loop quantum cosmology, developed from the framework of loop quantum gravity, proposes something different. In this approach, the Big Bang singularity is replaced by a quantum bounce. The universe did not begin in a singularity. It contracted from a previous state, reached a minimum size determined by the discrete quantum structure of spacetime, and then bounced into the expanding phase we observe. Before the Big Bang, in this picture, there was a contracting universe. The Big Bang was not the beginning of everything, but a transition from a contracting phase to an expanding one. And the cyclic cosmology of Paul Steinhardt and Neil Turok proposes that our universe is one of an infinite series of phases, each separated by a Big Bang, each driving the universe through cycles of expansion, structure formation, and eventual contraction. In their picture, The low entropy of our Big Bang is a consequence of the specific dynamics of the transition from the previous cycle. The improbable beginning is made less improbable by being embedded in a larger cyclic structure. Each of these proposals is speculative. None has been experimentally confirmed. But they share a common feature that I think is important. They all suggest that the first page of our universe's story may not be the first page of all stories, that the Big Bang was not the beginning of everything but the beginning of this chapter, that there may have been chapters before it, that the echo I have been describing may not be the only echo that has ever sounded. If that is right, then the universe has been producing echoes for much longer than 13.8 billion years, perhaps forever. Each beginning in an extraordinarily ordered state, each evolving through its Stelliferous Era, its local complexity, its self-awareness, in whatever form the specific constants of that universe permit, each eventually fading into the silence of maximum entropy, and then, through some mechanism we do not yet understand, beginning again. We do not know if any of these proposals is correct. We do not know if there were universes before ours or if there will be universes after. We do not know if the low entropy beginning of our Big Bang is an accident, an anthropic selection, or a consequence of a larger cyclic structure. But the question is not unanswerable in principle. It is a question about the structure of physical reality. And physical reality has a structure that better theoretical tools and better observations may eventually illuminate. There is something worth noting about the specific proposals I described. All of them, the Hartle-Hawking no-boundary wave function, the loop quantum bounce, the Steinhardt-Turok cyclic cosmology, share a feature with the block universe picture I have been developing. They all describe the universe as a complete mathematical structure with specific properties at every temporal location. Whether that structure has a first temporal location or extends infinitely into the past, whether it consists of a single cycle or infinitely many, the structure is complete. The story is written, all of it. Not just from the Big Bang to the heat death, but including whatever came before and whatever comes after. The no-boundary proposal is particularly interesting in this context because it suggests that the concept of before the Big Bang is not just unknowable, but inapplicable. The geometry of the no-boundary universe does not have a temporal direction in the region near its smooth endpoint. Time, as a well-defined coordinate, emerges gradually from the compact geometry, the way the concept of south gradually ceases to apply as you approach the South Pole. There is no first moment because there is no temporal direction to define a first. The story has no first page because at the beginning, pages are not yet the right concept. The story begins when the temporal geometry becomes clear enough to support narrative, which is to say, when time becomes a meaningful coordinate. And from that point forward, the story proceeds exactly as I have described, toward greater entropy, toward the heat death, toward the last page. Whether the universe has a before in the no-boundary picture or not, the echo I have been describing, the Stelliferous Era, is a specific region of the complete space-time structure, bounded on one side by the extraordinary beginning and on the other by the maximum entropy ending, self-contained, complete, and containing in its middle the specific physical process of minds becoming aware of the complete structure. We do not know if this is correct. We do not know if there were universes before ours or if there will be universes after. We do not know if the low entropy beginning of our Big Bang is an accident, an anthropic selection, or a consequence of a larger cyclic structure. But the question is not unanswerable in principle. It is a question about the structure of physical reality. And physical reality has a structure that better theoretical tools and better observations may eventually illuminate. Now, let me bring everything together because I have been building towards something and I want to arrive at it clearly. I want to say what I think the physics is actually telling us about the significance of living in the middle of this particular story. The entropy gradient from the extraordinarily improbable beginning to the maximally probable ending is the source of every process in the universe. Not just stars burning, not just organisms metabolizing, but also the development of the capacity to understand the gradient itself, the specific form of the low entropy beginning, combined with the specific values of the fundamental constants, produced a universe in which the gradient is not simply converted into radiation, but is channeled into increasingly complex structures. Structures capable of chemistry, structures capable of biology, structures capable of the specific kind of information processing we call consciousness. I want to say something about the specific physical process of consciousness in this context, because I think it connects to the gradient in a way that is not just metaphorical, but physically precise. Consciousness, whatever it is a process that maintains and processes information. It takes in signals from the environment, integrates them with stored information about the past, generates models of the present and predictions about the future, and uses those models to guide behavior. This process, the maintenance and manipulation of complex informational patterns, requires a thermodynamic gradient. It requires energy flowing through the system, being used to maintain the organized patterns against the constant pressure of thermal dissipation. Without the gradient, without energy flowing from a hot source to a cold sink, the information processing that we identify with consciousness would cease. Consciousness is thermodynamically expensive. It requires a steep gradient to sustain. The specific gradient that sustains human consciousness is the one flowing from the hot nuclear furnace of the sun through the Earth's biosphere into the cold blackness of space. Plants capture solar photons and store chemical energy. Animals, including humans, consume that chemical energy and use it to maintain the organized, low-entropy states of their bodies and brains. The electrical activity in your neurons, the ionic gradients that drive the signals, the protein synthesis that maintains the neural machinery, all of it is sustained by the thermodynamic gradient between the sun and space. You are, in a precise physical sense, an eddy in the solar wind, a local organization of matter maintained by the flow of energy from a hot source to a cold sink. This connection between consciousness and the thermodynamic gradient means that consciousness is not just in the universe, it is of the universe. It is a specific manifestation of the gradient, a specific way that the entropy gradient between the extraordinarily ordered beginning and the maximally disordered ending is being converted into something, not just heat, not just radiation, something that processes information about its own existence, something that models the gradient that produced it. And consciousness, specifically, has done something that no other physical process in the universe has done. It has looked at the gradient that produced it and described that gradient mathematically. The equations that describe the heat death, the second law of thermodynamics, the Schrödinger equation, the Einstein field equations, are patterns that minds discovered within the universe by observing it. They are the universe's self-description, developed by configurations of matter that are themselves products of the gradient the equations describe. The universe has, in the specific physical process of conscious observation and mathematical modeling, acquired the capacity to understand its own structure. And it is not just equations. The gradient has produced art, music, literature. These are physical processes, patterns of organized matter and energy that carry information about the universe from one mind to another, that create shared models of experience, that allow one configuration of the gradient to communicate with another. When Bach wrote the Goldberg variations, he was a configuration of the entropy gradient, creating an organized pattern of vibrations in air that could reorganize the neural activity of other configurations of the gradient producing in them something that resembles, however imperfectly, the experience he had while composing. The music is the gradient communicating with itself across time and space, using organized patterns of physical information. When a physicist derives the equations of thermodynamics, something similar happens. The physicist is a configuration of the gradient developing a mathematical model of the gradient. Other configurations, students, colleagues, future generations, read the derivation and reorganize their own neural patterns to include a representation of the gradient's behavior. The knowledge propagates, the self-model of the gradient improves, the universe knows a little more about itself than it did before. Both processes, art and science, are examples of the same fundamental phenomenon. The gradient organizing matter into configurations capable of creating and transmitting complex patterns of information. The